Okay, now in this portion of section 3.1, we're moving away from analytic and moving on towards a graphical approach. The derivative function gives us a relationship between x at one location and the slope of the tangent line to the function at that same x location. We can approximate what the derivative graph would look like by estimating slopes. And people are going to struggle with this unit only if you get too hung up on the approximation. So let's go ahead and take a look at example 1. We've got a function that's curved, and I've given you a couple of coordinate point locations. And for each of these, I'm going to estimate the x location, and then I'm going to estimate the slope at that location. And again, I'm making up these numbers, but they're good estimates. So at point A, I would say that that x has a value of -1. Now, in order to draw a tangent line, you start at coordinate point A and you move a little bit in one direction and a little bit in the other, and you would extend it out if you were to create a tangent line. Now, I'm going to look at this and I'm going to say, yep, that's a positive slope, and it's more than a 45-degree angle. I'm just going to call it approximately 10. Okay? Now, some people are like, whoa, where'd you get the 10 from? Don't worry about it, because I'm just approximating that it is a positive number. Okay? It's a positive large number. At coordinate point B, I'm going to call that x value -1/2, and the approximate slope at that, if I start at B and I move a little bit to the right and a little bit to the left, it's still a positive slope. It's still very steep, not quite as steep as the previous point. Okay, so I'm going to call it an 8. At coordinate point C, if I move a little bit to the left and a little bit to the right, we'll pretend that goes through point C. Okay, that is a horizontal tangent line, so that has a slope of 0. The coordinate point at C, I don't know, let's call it a third. No, maybe a fourth. Okay, it's pretty small. At location D, drawing your tangent line there, and that's about 1.5 maybe. And the slope this time is negative, and it looks to be probably about the same as at point B, but just in the negative, maybe a little less. So I'm going to call it a -6. At coordinate point E, again, we've got a horizontal tangent, so that should be 0. And I'm going to call that coordinate point 2.5. At F, sketching it in, I'm going to say that that looks pretty close to what the slope at B was. And that coordinate point for F was 3. And at point B it had a slope of 8, so I'm going to give it the same slope. Again, it's approximate. Let me scooch up just a little bit. Now for G, our last guy, if I was to sketch that in, that would be approximately 3.5 for the x coordinate, and then for the slope, it looks about the same as A, so I'm going to give it another value of 10. Okay, now what does this do for us? On this coordinate plane, I'm going to sketch the x coordinate and the approximate slope. So again, look at this. Let's go ahead and actually call this upper function. Let's call this f of x, and this would be x. And we'll be very clear that for our other function, it would be called f prime of x then. And this would still be the x coordinate. Okay, so on our chart, let's call this guy, this is f prime of x. Okay, so when you sketch a derivative, you are literally plotting the slopes at infinitely many locations for a function, but we're only going to do further a couple representative points. At coordinate point A, that was x at -1, and we had a slope of 10, which means we are going to plot the coordinate point -1, 10. Now, I obviously didn't give enough room, so I'm just going to make a coordinate point way up here somewhere. At x equals a -1/2, I would have 8, so that would be up here. It would be higher than that, actually. At C is 1/4, I would have a point of 0. At D is 1.5, I've got a negative 6 value. Let me slide this guy. At 1.5, I've got a negative 6, so that would be down here somewhere. At 2.5, I had a slope of 0, so that's going to be 2 comma 0. At 3, I've got a value of 8, so it goes way back up, and then it goes way back up again. Okay. So if I was to sketch this smoothly as best I can, I'm getting a function that looks something like this. Okay? Again, it's completely approximate. Don't get hung up on the slopes that I randomly chose. As long as you kind of compare them to the previous point that you were looking at, you're going to get a sketch that's pretty accurate. So let's go on to the next page. There are a couple techniques that you can follow to help you sketch the derivative graph a little bit quicker. Since f prime of x represents the slopes of the tangent lines, we can start off by finding any location where the tangent line would be horizontal. Hence the slope would be 0. For any f of x that is decreasing, the slopes would be negative. And because the slope is represented by f prime, if we're sketching a graph of f prime, it would have to be below the x-axis. Likewise, if f of x is increasing, those slopes would be positive. And then f prime of x would have to be above the x-axis because that would represent positive values. Okay? So again, if f of x is increasing, the derivative would be positive. If f of x is decreasing, the derivative would be negative. And then if f of x is constant, it would be completely horizontal, and then f prime would have a 0 slope. So then the graph would be on the x-axis. So let's go ahead and take a look at a piecewise function, and we're going to sketch the graph on the derivative on the axis to the right. So the first thing I'm going to have you do is get in the habit of labeling your axes. This would become f prime of x because my given function was called f of x. And if I label the x-axes a little bit, those would be x and x. Now, because this is linear, you can calculate the exact slope for every segment of this function. So in between 0 and 1, it's rising 2, and it's going across by 1. So that would be a slope of 2. Okay, so the slope equals 2. For the segment from x equals 1 until x equals 4, again, we're rising up a value of 1 here, but we're running a value of 3. So here our slope is only a third. In between 4 and 6, there's no change in the y value, so the slope would be 0. And then for this guy, we are going down 3 and over 2. So this is a negative 3/2 for the slope. So how does that correlate? Well, for every x value, in between 0 and 1, it has to have a derivative value of 2. So that would look something like this. Now the question comes, what do you do at the endpoints? And we're going to talk about this in class, but the left endpoint is going to be filled in, and the right endpoint is actually going to be an open circle. And we'll talk about this again, like I said, in class. In between 1 and 4, we have a slope of a third. So I'm going to come down here. It's going to be an open circle, and we're going to go all the way until we get to x equals 4. And then we've got a slope of 0. So right below the 4, sorry, this is kind of hard here, we're going to go from 4 until 6 on the x-axis. And then in between 6 and 8, we've got a negative 3/2, which is negative 1.5, all the way until 8, and we've got a closed circle there. Okay? So this ends up looking like a big stepping function at every location where the slope changes drastically from, for example, at x equal 1, it changed from a slope of 2 to a slope of 1/3, and it did it at that instant. That's why at x equals 2, it's going to be an open circle. Let's go ahead and do the next example. Okay. For linear functions, we can plot exact values of the derivative easily. But if it's a nonlinear function, we're going to have to estimate those slopes. Okay, so think about it. Why would you have to estimate slopes for nonlinear functions? If it's not linear, you can't calculate it by doing rise over run. Every location is going to have a different slope value because of the curve. Okay, one of the things I need to point out, two things actually on this example. The first thing is the functions all have a domain of negative infinity to infinity. I got these graphics from a book or online, I can't remember, but so I cropped them and put them in, but they don't have the arrows. So that's the first thing, is all of these functions continue on. The second thing is the graph of the original function and the graph of the derivative, these two have different coordinate or different grids. Okay, so here every grid marker is counting as 1. Here every grid marker is counting as 1, but I've got them labeled, so every tick mark here is a half, and here every tick mark is 1. Okay, so I think I've babbled on enough. Let's go. When you graph the derivative, the first thing is to label the axes. This is going to be h prime of x, and this would be x. Okay. The first thing that I mentioned would be helpful for you to do if you're graphing a derivative is to find the locations where the derivative would be 0. And that's any location on your function that has a horizontal tangent. So I'm going to point out that that guy would have a horizontal tangent, so would that one, and so would this location. All of those have horizontal tangents. At those exact locations of x, the derivative would be 0. Okay, so I'm going to locate those same locations on the graph on the right, and I'm going to plot them. At x equals, that would be a negative 1/2, the derivative would be 0. Again, I'm graphing x versus the derivative. Sounds like a good title for a movie, huh? At x equals 1, we also have a slope of 0 on our h of x function, and at x equals 3. Okay, so I've got 3 zeros on my derivative graph because I have 3 locations on my h of x function where the tangents are horizontal, and hence the slopes are 0. Now, the next part, all you're going to do is take a look at everywhere that the function is increasing. That means when you move from left to right across the graph, the y values are going up. Okay, so I'm noticing that from negative infinity up until negative 1/2, and then from 1 up until 3. These are positive slopes, which indicates my derivative graph must be above the x-axis. Some people like to choose a couple representative points and just draw tangent lines, just so you can get a sense of what's going to happen. Okay, so I'm going to pick 2 of them that are to the left of that first at x equals negative 1/2. I'm going to pick 2 points to the left of it. So it looks at about negative 1.7. If I draw a tangent line in here, that's a very big positive number. Maybe like, I don't know, a 6, 7, 8, something like that. So at negative 1.7, I'm going to plot something that is very positive. At x equals negative 1.5, I again have positive, but it's not quite as positive. So at negative 1.5, I'm going to pick a next value there. It has to be smooth and connected, so it's going to come down and touch that point. In between negative 1/2 and positive 1, I've got negative slopes that become more negative, and then they kind of flatten out, and then they becomes less negative. So more negative, and then less negative. That should come back up and touch that point. And then in between x equals 1 and x equals 3, it's a positive slope that becomes more positive and then becomes less positive. So a little bit more, less. And then you'll notice after that it's negative but becoming more and more negative. So a little bit negative becoming more and more negative. Okay. So The functions that are curved are much more difficult, obviously, than the linear functions. We like the linear ones. If you take a look at g of x, first thing I'm going to do is label this as g prime of x. This would be x, and this would be x. And I'm going to put arrows on this guy. And this is linear, so I can calculate the exact slope. Every tick mark counts for 1, so it's going down 1 over 1, down 1 over 1, down 1 over 1, all the way up until x equals 0. At x equals 0, then it changes to up 1 over 1. And that tells us that at x equals 0, it is changing, and it's changing quickly, so it's not going to have a derivative there. But everything to the left of x equals 0 has a slope. Let's try that again. Okay, that might be my favorite when it jumps around like that. Sorry about that. That means that the slope is -1, so I drew it the wrong way. There we go. The slope is -1 this entire time. M equals -1. Here we've got a slope of +1, so we're just going to have a slope. All of the slope values to the right of x equals 0 are showing a slope value of 1, so that's why g prime is 1 the entire time from x equals 0 until infinity. So I am guaranteeing you will probably have questions on the derivative graphs, especially when they are not linear, but on the next page you will see you've got some practice problems to try. So give those a shot, and I'll see you in class tomorrow.